Hi and welcome. I'm Rebecca Weaver. We're looking at section 6.3, the definite integral and the area under a graph. Woo! So let's look at that definition. Area under graph of f of x from a to b. We've got some function and the function maybe goes up and then down, and it is bounded from a to b and that function, and we want to know that area that's underneath that curve. Now, if f of x is a continuous, non-negative function on the interval from a to b inclusively, we refer to the area of the region as shown as the area under the curve, under the graph of f of x from a to b, or the area bounded by the graph of f of x, the x-axis and the vertical lines at x equal a and x equal b. Theorem for this says that if f of x is a continuous non-negative function on the interval from a to b inclusively, then the area under the graph of f of x from a to b is equal to the definite integral of f from a to b. So we have that the area under the graph from a to b is the integral from a to b of f of x dx, and this is evaluated with the antiderivative by plugging in b, subtracting the antiderivative, plugging in a. So let's look at an example of this. We're going to use Theorem 1 to compute the area of the shaded region under the graph of f of x equals 3x squared plus e to the x from x equal -1 to x equal 1. So let's get started with that. We need to write that definite integral. So it'll be the definite integral from -1 to 1 of 3x squared plus e to the x. We're going to find the antiderivative of that, which would be x cubed plus e to the x, and then we'll substitute in the 1 and subtracting off our substitution of -1. With that, our exact answer would be 2 plus e minus 1 all over e, which approximates to 4.35. So that's the approximate area. In Riemann sums, what we do is we get about what that area is by breaking up our interval into partitions. So we'll learn to get an estimate of the area under the graph of f of x from a to b by dividing the interval into partitions or subintervals, each one having the width, and we're just going to break them up equally, and this delta x equals b minus a over n just breaks it all up into equal partitions. And so in this case, we let our n be 4, or we wanted 4 partitions. A Riemann sum is the sum of the areas of the rectangles generated above. So you have to figure out what the size of those rectangles is, get the area of each, and then you would just add that together to get that approximate area under that curve. So we're going to use a Riemann sum to approximate the area under the curve of f of x on this given interval using midpoints. So we need to get our intervals, and then we're going to break it into midpoints of f of x equals x squared from -2 to 2, where n is 4. So the partition of -2 to 2 with n equal 4 is going to be this little graph here. So we're going to break it up into 4 sections, and we want to know the midpoint of each section. So the length of each subinterval is 1. That's very convenient. It's really nice. And so if that length is 1, in between, like this would be a 0 here and this would be a 1, so in between would be those half marks. Observe that the first midpoint is delta x over 2 units from the left endpoint, and the midpoints themselves are delta x units apart. Meaning you can just, it's on the half, so just add 1 to get to the others. The first midpoint is x1 equals -2 plus delta x over 2, so that would be -2 plus 0.5, or -1.5. The subsequent midpoints are found by adding that delta x equal 1. So here's our midpoints here. The corresponding estimate for the area under the graph of f of x is you're just going to plug in each of those different amounts. Now the delta x is the width of each of those rectangles, so that's a 1. And then we plug in the -1.5, the -0.5, and the 0.5 and the 1.5 into our function, get those values, and then crunch our numbers. And we get a 5. So we estimate the area to be 5 square units. So here is our estimate of the area under the curve. And you can see it's a pretty good estimate. If you were to look at this, I'm missing this piece here and this piece here, but this one a little over, so it's a fairly good estimate. So let's use the Riemann sum to approximate the area under the graph of f of x on the given interval using left endpoints for our subintervals. So we're going to use our left endpoints for f of x equals x cubed on the interval from 1 to 3 where n is 5. So if we break up our partition from 1 to 3 with 5 subintervals or 5 rectangles, the length of each, plugging this in, is going to be 0.4. So here we have our interval from 1 to 3, breaking it up into adding 0.4 each time to get to that 3. So our corresponding Riemann sum is each of these rectangles is then 0.4 in width, and so you'll just plug in the 1, the 1.4, the 1.8, the 2.2, and 2.6 into your original function, and what we'll end up with is 15.12, which means that the area is 15.12 square units, or that's its estimate. Here's a picture of that I've got for you. So I can see that this estimate using the left endpoints, these left endpoints of each of those subintervals, this estimate's going to be a little under what it ought to be. Our fundamental theorem of calculus, Theorem 2, let f be a continuous function on the interval as a closed interval from a to b with the antiderivative, capital F. Then the Riemann sums approach to the definite interval of f on that closed interval a to b as the number of subintervals increases indefinitely. That is, the limit as the width of that subinterval goes to 0 of that Riemann sum gets closer and closer to that definite integral. So we're going to use the fundamental theorem of calculus to calculate the following integral. Now, an antiderivative of 3x to the 1/3 minus 1 minus e to the 0.5x is going to be, and we're doing this from 0 to 1, is capital F of x equals 9 over 4x to the 4/3 minus x minus 2 e to the 0.5x. Therefore, by the fundamental theorem of calculus, I'm going to just plug in a 1 and 0 to that antiderivative. And there we are, plugging in the 1 and 0. We're going to crunch these numbers, and we're going to end up with negative 0.047. Nice. So let's do an example with heat diffusion. We have some food, and it's placed in the freezer. After T hours, the temperature of the food is dropping at a rate of R of T degrees Fahrenheit per hour, where R of T equals 12 plus 4 all over T plus 3 quantity squared. Let's compute the area under the graph of y equals RT over the interval from 0 to 2. What does the area in part A represent? Okay, so to compute the area under the graph of y equals R of T over the interval 0 to 2 inclusively, we're just going to evaluate the following. The definite integral from 0 to 2 of our function 12 plus 4 all over T plus 3 quantity squared with respect to T. When we evaluate this from 0 to 2, we end up with 24.533. Since the area under the graph can represent the amount of change in a quantity, the area in part A represents the amount of change in the temperature between hour T equals 0 and hour T equal 2. That is, the change is 24.53 degrees Fahrenheit. All right, if you have any questions with this section, be sure and email me, rweaver10@alaska.edu, and have a wonderful day.